In section 5.5, we'll learn about one new set of formulas called the double angle formulas. And these formulas, if you look at the bottom of this slide, deal with angles whose argument is different than x. So on the left-hand side, you see the argument is 2x, and on the right-hand side, we can reduce that down so that the argument is just a trig function in terms of x. And another thing to notice is that cosine of 2x has three different equivalent expressions, all which will give you the same result. Okay? And those just come from rearranging using the Pythagorean identity. So we're going to be able to find the sine, cosine, and tangent of double angles and rewrite and solve different trig equations using these expressions. So first, let's take a shot at some derivations, because I think it's kind of cool to see where these formulas come from. So my hint is that we're going to use a sum formula, the ones that we learned in section 5.4. So to start, just to recall, we have sine of a plus b equals sine a cosine b plus cosine a sine b. So if I'm trying to derive the sine of 2x, okay, I'm going to notice that that's equal to the sine of x plus x. X plus x gives me 2x. And now that means a is x and b is also x. So I'm going to fill that in to the formula I have up above in black. So I've got sine x cosine x plus cosine x sine x. And in total, there's two of those terms, so I get 2 sine x cosine x. And on the first slide, you can see that's the same formula that we had. We'll do a similar process for cosine. Got cosine of a plus b. And our formula for this would be cosine a cosine b minus sine a sine b. So here we have sine of 2x, or sorry, cosine of 2x. Which similarly would be cosine of x plus x, where a and b are both x, and that's going to give us cos x times cos x minus sine x times sine x, which is equal to cosine squared x minus sine squared x. So that's the first form of cosine of 2x that we have for our identities. The other two forms, if you plug in for either sine squared or cosine squared with the Pythagorean identity, you can derive those. And tangent of 2x we could do with a very similar process. So our first example, we're given the triangle on the right, where our angle theta has an adjacent side of 3, an opposite side of 2, and an unknown hypotenuse. And we're asked to find the sine, the cosine, and the tangent of twice the angle theta. So the angle theta given in the triangle is just 1 theta. So we're trying to find the sine, cosine, and tangent of 2 theta. Okay? So we're going to start by finding the hypotenuse using the Pythagorean theorem. So this should be pretty straightforward. 3 squared plus 2 squared is equal to the hypotenuse squared. So that's just the Pythagorean theorem. And this will give us 9 plus 4 equals h squared. So 13 equals h squared. Taking the square root, that gives us h is equal to the square root of 13. Okay. So now let's use trig ratios. We're going to find what the sine, cosine, and tangent of theta is, and that's just going to be using our opposite, adjacent, and hypotenuse values. So to start out, sine of theta is opposite over hypotenuse, which would give us 2 over root 13. And we're just going to rationalize that real quick. And it gives us sine of theta equal to 2 root 13. Oops, can't quite read that. 2 root 13 all over 13. Cosine of theta is equal to adjacent over hypotenuse. And that's going to give us 3 over the square root of 13, which we're going to rationalize and get cosine theta equals 3 root 13 all over 13. And last but not least, the easy one, tangent of theta is equal to opposite over adjacent, which would give us 2 over 3. So tangent theta is 2 over 3. So we've got those three values. We're going to use them because if you notice in your identities in the first page, we're going to have to plug in sine of theta, cosine of theta, and tangent of theta, and then simplify. So step 3, our final step, we want to evaluate what sine of 2 theta is. Well, our formula says it's 2 times sine of theta times cosine of theta, which would give us 2. And then looking on the previous page, we've got 2 root 13 over 13 and 3 root 13 over 13. So this will give me 2 times 2 times 3. The square root of 13 is combined to give me a 13. On the bottom, I've still got 13 times 13. So I'm going to cancel out one of those 13s, and I'm left with 12 over 13. So sine of 2 theta is 12 over 13. So let's switch colors here. Cosine of 2 theta, we'll use that first identity. It's cosine squared theta minus sine squared theta. So this is going to give us 3 root 13 over 13 squared minus 2 root 13 over 13 squared. Simplifying, we get 9 times 13 over 13 squared. I'm going to write as 13 times 13. Subtracting off 4 times 13 over 13 times 13. And again, we can cancel 113 in each of these fractions. And that's going to leave us with 9 thirteenths minus 4 thirteenths, which is equal to 5 thirteenths. So cosine of 2 theta is equal to 5 thirteenths. And again, last but not least, we've got tangent of theta. Sorry, tangent of 2 theta. Our formula for this is a little bit different. It's 2 times the tangent of theta over 1 minus tangent squared theta. So recalling from the previous step 2, tangent of theta is equal to 2/3. So we're going to plug in 2 times 2/3 over 1 minus 2/3 squared. And that gives me 4/3 on the top and 1 minus 4/9 on the bottom, which would give me 4/3. We're dividing by a fraction, and this fraction happens to be 5/9. So if we're dividing by 5/9, we're multiplying by 9 over 5, the reciprocal. And then we can simplify. We've got this 3 and this 9 can cancel out, and we're left with a 3 here. So 4 times 3 gives me 12 over 5. So tangent of 2 theta equals 12 over 5. So notice our three values. We've got sine, cosine, and tangent of 2 theta. Our values are 5, 12, and 13. So that's one of our Pythagorean triples. Once you find sine and cosine, you could just use the identity that tangent is equal to sine over cosine, and then simplify. Our second example, we're going to solve the multiple angle equation. So we have cosine of x, and we also have sine of 2x. So in order to solve this, we need to turn the sine of 2x term into a term with only sine and cosine of x. So we're going to use the double angle formula. So when we plug that in, we still have our 2 cosine of x, and then plus sine of 2x is 2 sine x cosine x, and that is equal to 0. So now I want to factor out. I've got a 2 times cosine of x in common, so let's factor that out. Got 2 cosine of x, and I'm left with 1 plus sine of x equal to 0. So I'm in factored form, so I'm going to set each factor equal to 0. So the first one gives me 2 cosine x equals 0. If I divide by 2, I just get cosine of x equals 0. Looking on the unit circle, that would be straight up or straight down. So that's x equals pi over 2 plus 2 pi n, and x equals 3 pi over 2 plus 2 pi n. So there's our first two values, and our other values are going to come from this expression, where 1 plus sine of x equals 0. We subtract 1, we get sine of x equals negative 1. And this also happens to be on the negative y-axis at x equals 3 pi over 2 plus 2 pi n. So since we already wrote that over here in the box, then we're good to go, and we've had all of our answers. Our third and final example is simply rewriting an equation using the double angle formula. So we want to rewrite this equation into something that's a little bit more condensed, and we're going to see why we do that at the end of the problem. So first I'm just going to notice that there's a 2 in common with these terms. So if we factor out that 2, we're left with 2 cosine squared x minus 1. Okay? And this, in parentheses, happens to be a double angle for cosine. So what we're going to do next is the 2 is still multiplying it, but now it's 2 times the cosine of 2x. And that's really as far as you can go. We're going to stop there. But here's why we did this. Okay? This 2 multiplying our x, we can really write as y equals 2 times cosine of x over 1/2. So if we're talking about the transformation form, our b value is 1/2, which means our period factor is also 1/2. All right? So why do we do this? Well, let's see. What do I want to say? We recognize this as a cosine graph with amplitude of 2. So it's stretched vertically by 2, a factor of 2, with that 2 multiplying out in front. And period factor of 1/2, which would make the period pi instead of 2 pi. Therefore, we can easily graph it. Because we haven't learned anything about what the squared graph would look like. So if you start with the equation up here, where we have cosine squared of x, we really have no clue what that graph is going to look like. So once we use our double angle formula to simplify it down, we get something that we would know how to graph. So there's 2 problems for you to try. The first one, you're just rewriting, using the formula to rewrite, sort of like the example 3. And number 2, we're given a value of tangent, and you're supposed to find sine of 2 theta, cosine of 2 theta, and tangent of 2 theta, like example 1. So you're going to want to go through all those steps that we did in example 1. So give those a shot and bring those into class.